Hello again to EMRS TV, and we are very honored to have here Professor Klaus von Klittzing, a Nobel Laureate in Physics. Welcome, and thanks for being here with us today.
Thank you for the invitation.
So, my first question is regarding the Nobel Prize, and so you developed the quantum Hall effect, if I'm correct, and only 5 years later you won the Nobel Prize, which is a very short period of time. So did you know right from the start that your invention was this groundbreaking?
First of all, you should never work for the Nobel Prize because the probability is small and one is disappointed. And my discovery was really unexpected. So I worked on materials, on the most important device in microelectronics. Everyone has a computer, a cell phone, and I wanted to understand the microscopic properties. And I have done basic science to understand how electrons are moving, how can I make the device smaller, faster. And I worked with different companies, electronic companies together. And then in the night of the 5th February 1980, I know exactly at 2 o'clock in the morning, I have done experiments, and I remembered that I saw something which was identical. I saw at the other sample from other country. I worked with England, with the United States, with Germany. And then I've asked the question, what's the reason that I see something for independent samples? And then within 10 minutes it became clear that something new was seen. And this happens very often for Nobel Prize winners. They unexpected discoveries. They work on something and then they need the freedom to look at the other directions and to ask new questions. So I asked a new question, and then in a half an hour I saw, okay, there's something fundamentally new. But I didn't think at this time on the Nobel Prize. But already half a year later, I gave a talk at a conference, and somebody from Korea came to me and said, this will be a Nobel Prize. So, and my discovery was a new type of electrical resistance. Normally a resistor has any values depending on the length of a wire, cross-section material. And I found something which is independent of the material, which has always the same value. So like if somebody measures velocities, you have different velocity of a car, for an airplane. But if you go to velocity of light, of all electromagnetic radiation, then you have the same velocity, the velocity of light. This is one of the fundamental constants, which is everywhere the same in the universe. And I discovered a new type of electrical resistance, which is independent of material, everywhere the same in the universe, and only depending on fundamental constant. And the fundamental constant today called von Klittzing constant, but is related to the so-called Planck constant and elementary charge. And this was really so unexpected that nobody believes it. Even I had difficulties to publish it, but then it was repeated immediately by other countries. And already 5 years later, I got the Nobel Prize for this because everyone saw this is a breakthrough.
It's a big thing, okay, thanks. And how did it change your life, the Nobel Prize, and also how did it influence your further research into the topic?
Okay, without Nobel Prize, I wouldn't be invited to give here an interview and to attend a nice conference in Nice, yes, so you get many, many invitations. No, there's, I think, positive, negative aspects. First of all, your support is better. You get good students, you have a reputation, and you have not to write proposals. And as a Max Planck director, anyway, I have quite good freedom to do my research. So the boundary conditions for the scientific work are much better if you get the Nobel Prize. But you have suddenly some additional responsibilities outside your research field. So everyone expects you know everything, but this is not true. So you know something about your field, you are specialized in this field. But suddenly they ask you, oh, do you believe in global warming? And what are the consequences? And should we fight against this problem, human rights problems? You have responsibilities as a Nobel Prize winner, because if you tell something, you have some impact. So suddenly you have to decide whether you have to do some service also for these questions, yes, many human rights questions. This is a burden if you know that scientists which just say the truth go to prison, yes. So it's a positive, negative side, but overall is something special. But when I got the telephone call that I got the Nobel Prize, I had the feeling, okay, now it goes back, downhill because this is the top, yes, the Nobel Prize. What happens afterwards, yes? But I have the idea to have an environment for scientists to be creative, and it gives them good opportunity because I, as a student, my professor gave me the freedom to do science, and I'm trying to give also my students this freedom and independence. I never say you have to do it. I want to have the atmosphere that they are creative.
So this is also the core of science, right? To explore what you really want to explore.
Yeah.
Right. So, and how does it bring you into EMRS? So this is materials research, so can you give us the bridge to your field of research? So where's the interconnection also to the other symposia that we've seen here?
Okay, the discovery is always connected to semiconductor physics or some materials, graphene, gallium arsenide, silicon are the most important materials. Even if the final result of my discovery is independent of the material, you need the material as a substrate, and all the different superconductors, they have many, many different applications, and in the same way also the so-called two-dimensional materials. This is a new quality today in material science, that we have very thin layer, which is even only one atomic thickness for graphene. If you write with a pencil on a paper, you're rubbing off graphene carbon sheets. And today we are able to prepare these so-called two-dimensional systems, and they have new physics, qualitatively new physics, which is quite different from the three-dimensional world for our daily life. And therefore a lot of research activities are now in these so-called two-dimensional systems. And if you go to new quantum phenomena, then you see many of them in two-dimensional systems.
So what you detected has also the large impact on the system of units. So can you probably explain what it is about and give us some background on this?
Yes, 2019 is a very, very important year, because 10 days ago, we are now in May 2019, there was a decision that worldwide we have a new system of units for our measurements, kilogram, meter, second, and all these will be based on fundamental constants, or constants of nature, because they are everywhere the same in the universe. And therefore they are stable. So in Japan, in Europe, in America, they have the same units, and if you can relate them to some measurement system, then you have everywhere the same basis. And now we have changed our system not to an artifact. The kilogram was up to now a piece of metal in Paris. In the future, the Planck constant will be the basis. And since I mentioned already that my discovery is connected to fundamental constant, they was the driving force, my discovery, to have this replacement of our international system of units. So therefore, in the future, all these so-called 7 base units, where we can every measurement can be traced back to these 7 base units, can be or are based on fundamental constants, so therefore more stable, more reliable than our system before.
And will this also change the life of all the people, so someone who is not a scientist? So what impact does it have?
No, we try to have this transition in a way that in the daily life, if you go shopping, then you will get still a kilogram, because at the day of the change, we adjusted in such a way that we have a continuous transition, but in former time, our kilogram was not stable. For example, the metal piece is not stable because some gas is diffusing out, and it becomes lighter with time. But in the future, fundamental constants are stable, because we don't know any correction to the stability of fundamental constant. Therefore, we have a much better, more stable system. But in the daily life, only for very high precision measurement, the ohm and the volt are slightly changing, but you will not see it directly. Don't worry.
Okay. And my last question is regarding your vision for the future. Do you have something that you're currently working on, or do you envision something that, or do you have still a dream that you want to achieve?
Yes, so quantum is everywhere, and we have in Europe also special programs for quantum technology. Quantum, in principle, everything is quantum. In chemistry, you can say everything is quantum. Optics is a lot of quantum, and you hear sometimes quantum computer, and there are some special properties of these two-dimensional systems. And I want to explore really whether these so-called strange quantum phenomena can be really controlled in these nanoelectronic devices. So I have the vision to see the fundamentals of the quantum computer in principle. There are so-called topological phenomena, and a lot of research is necessary, but we need time. So you cannot expect that in 3 times you can buy something in this field, but there's very fundamental research behind this.
But someday we may be able to.
Yes, I'm sure that our knowledge always increases, and if we increase the knowledge, we will apply it also. But I don't know. I never say this will happen in 10 years, because if you look back, nobody expected these rapid changes in our daily life, and predictions are so difficult. In science, in basic science, unfortunately, I'm able to work in basic science. I increase our knowledge at the limit of our present knowledge, and there's always something unexpected.
Well, thank you so much for sharing your insights.
Thank you.
Thank you.